Last class we discussed about the selection and the projection operation, right? So in this class we are going to discuss about the join operations. Okay, so to identify different access path, most selective access path, and the appropriate algorithm for that to perform the join operation if the query contains the join operation. Now what is the join operation? Now when we join, when we have more than one table or one relation from which the tuples need to be retrieved, okay, then there will be some joining conditions in that. Suppose if we have a query like this, select star from reserves are sailor S where the R dot SID is equal to S dot SID. So when we have such kind of joining condition as specified here, okay, to retrieve the tuples from more than one relation, then we have to perform the joining operation. Now here is an equijoint where we have equality to retrieve the tuples, right? So before going into joining operation, suppose if we have some two relations R and S, for example, we'll consider two relations R and S, and we consider R to be having m number of pages and S to be having n number of pages. Okay, so it is the, and for this TP, suppose TP is the small is the number of tuples that is there in each of the pages of the relation R, and suppose Tn is the small n subscript is the number of tuples that are there in the each page of the S relation. Okay, so considering this structure, we'll basically go for the identification of the algorithm of the particular relation. Okay, so let us consider this to be better. It will be if we consider this as PR PS, where PR represents the number of tuples in each page of the relation R. PS represents the number of tuples in each page of relation S. Okay, and how many pages are there in each relation? Suppose we are considering m number of pages in R relation and number of pages in the S relation. Now considering this, the first algorithm that we will be discussing to perform the join operation, the nested loop join to is the first algorithm that we will be discussing. Okay. Now what is a nested loop join? It's like for every tuple R, for each tuple R in the relation R, okay, capital R, and for each tuple S, small s, in the relation identified by the capital S, what we'll do, we'll basically compare each of the inner relation tuples with the outer relation tuple. Okay, so we'll basically consider one tuple from the outer relation, and we'll iterate through the entire tuples of the relation S to identify those tuples, any tuple, if any tuple have the condition, meets the condition Ri equal to Sj. Okay, so if this meets the condition, then add this particular combination of the tuples in the result relation. Okay, in the resultant relation. So for every tuple in the outer relation, we'll scan through the entire tuple list of the inner relation, okay, to identify the matching tuple given the condition that Ri equal to Sj. And if that particular condition matches, then we'll write that tuple to the result relations, okay, output relations. So that is what the nested loop join condition algorithm works like. You know, that is the way the nested loop join algorithm works. Okay. Now, if we have the cost of this algorithm is, how much will be the cost? For every, see, the outer relation M has to be scanned once. So we know that there are M number of pages in the outer relations. So you need to have, there is the M IO operation to retrieve all the pages of the outer relation. So you need to have the M number of IOs, right, to get the outer relation. Now for each tuple, so how many number of times you will be scanning the S relation? You will be scanning the S relation is by, because for each tuple of R you are scanning the entire S relation. So PR for each tuple into the number of pages of the outer relation, right? So this much number of time you are scanning the S, right, into the number of pages of the S relation. So it is basically M plus this PR, the number of tuple in the outer relation, number of pages in the outer relation, number of pages in the inner relation. So this much number of IO operations you need to perform. So this is the cost of performing this algorithm. Okay. Now, if suppose M is equal to 1000, right, and suppose PR, the number of tuples in the each page of the R relation is equal to 100, and N, the number of pages, is suppose in the S relation is 500. Okay, given this we can find out the cost of this particular algorithm, cost of executing this algorithm. So what will be the cost of algorithm? This algorithm 1000 plus what is PR? 100, right? What is 1000 into 500? Okay, so this is 1000 plus 5 into 10 to the power 7. Okay, this is the total cost of executing this particular algorithm. This much number of IOs will be required. So this is the total number of IOs, okay, to execute this algorithm. So this becomes the cost. Now, to improve upon this algorithm, because this is not a very efficient algorithm, given you can see the huge number of IOs is required to perform this kind of, you know, if you directly perform the inner looping inside the outer looping for each of the tuple, it's better if we can consider the buffer space, because this is not going to utilize the buffer space of the computer efficiently. Okay, to better utilize the buffer space, we can actually go for a different kind of algorithm, which is known as the block nested loop join. Okay, block nested loop join. So in the block nested loop join, before going into block nested loop join, let me tell you, to utilize the buffer space, suppose the inner relation, a particular relation is small, one particular relation, suppose the relation R is not that big, okay, number of tuples are not that huge. So what we can do, we can transfer the entire relation R to the buffer space, okay, provided there are two other extra pages. Why those two other extra pages are required in the buffer space is, one is to read the one page at a time from the outer relation, another page is to write the output of the joining. Okay, so there are provided two extra pages. If suppose there are B number of pages in the buffer space, okay, then we can, if the smaller relation is sufficiently not that big to be accommodated inside the bigger relation, then we can use the B minus 2 number of pages to read on the smaller relation. Suppose the smaller relation is R. Okay, so we can use this b minus 2 number of buffer spaces here to get the inner relation into the buffer space. Extra 2 pages, which are actually the other 2 pages, because we are considering out of the b buffer pages, we are considering b minus 2 buffer pages. So extra 2 pages, one can be used to get each of the page of the outer relation, and one page is to write the output of the joining. Okay, so this way we can make it efficient, because once we have it in the buffer space, the number of IOs required gets drastically reduced. Okay, but we are not fortunate enough to get this kind of situation often, because both the relations may be big enough actually, or it may be large enough to accommodate in the buffer space. But the advantage of this block nested loop join, that is to use the buffer space, can be utilized by dividing a relation into certain blocks. Okay, instead of transferring entire data of a particular relation to the buffer space, if it cannot be accommodated, what we can do, we can break up the relation into some blocks, such that each of the block can be accommodated in b minus 2 number of pages. Okay, suppose the relation R is big enough, but what we can do, we can break the relation R into certain blocks, and each block can be accommodated into b minus 2 number of pages. Okay, the same concept can be used to process the blocks one by one of the one relation. Okay, and that can be used as the inner relation, whereas the outer relation pages can be brought one page at a time from the extra 2 pages that we have. Okay, and one page can be used to write the outputs. Okay, so another thing can be done is that once we bring this in terms of the blocks, okay, the entire relation that you bring in to the buffer space can be converted into a hash table. Actually, hash table make it more efficient. Okay, so that can be converted into that can be converted into a in-memory hash table, and you can utilize the hash table instead of using the original relation. Okay, so for each block in b minus 2 number of pages, because now we know that it has been divided into blocks and we are reading one block at a time to the buffer space. So for each block in b minus 2 pages of R, okay, what we will do, and for each page S, because we are bringing one page at a time from the extra 2 pages. Okay, so we are bringing a page for each block. Block is in the buffer space. So for each block, we are basically reading one page at a time from the relation, from the S relation, which is not in the buffer, and then what we do, we basically find all matching in memory tuples where R, that is one tuple at a time from the block, that is the outer loop here. Okay, from the R block, and S, that is the page which has been brought from the S relation, and then if they matches this condition where R equal to S, then we write the results, that is add R as RS to the result. Okay, so that way, instead of doing it tuple by tuple, if we do in terms of the block, the number of, the efficiency of the query increases drastically. That is, we can see how it actually increases. Let us see with an example here. Okay, now total cost of this strategy can be calculated as the cost m IOs for reading R, because we know that there are m number of pages in the relation R. Okay, so we require m IOs even if we are reading actually block by block. Actually, what we are doing, we are breaking up those number of pages into certain blocks, right? So actually we are reading those m number of pages only. So there are m IOs for the relation R, which has been divided into blocks, right? So we are basically reading m IOs because we are reading all the pages, even though we are bringing it to the buffer block by block. Okay. After that, for each block, we are scanning the S relation. So how many times we are scanning the S relation here? It is scanned, that is M by B minus 2 number of times, right? So B minus 2 is the number of pages in the buffer, right? So it is the total pages of the relation R divided by the B minus 2, and this gives you the number of times you are scanning the S, right? So it is S is scan, a total number of time is M divided by B minus 2, and each scan here cost you how many times of IO, because you are basically scanning the S relation M by B minus 2 number of times, and each scan will cost you n IOs, because there are n number of pages in the relation S, right? So it will cost you n IOs. So total cost or total number of IO operation required for this particular algorithm is, the relation M is scanned M number of times because there are M pages, relation S contains n pages, right, into, that is M divided by B minus 2, that is the number of pages in the buffer space that you are using to read the block. Okay, so this becomes the total number of IOs required to perform this algorithm. Okay, so now let us take an example to see how it works. Okay, say if the reserve is chosen as the outer relation. Okay, now the reserve, we know how many pages are there in the reserve. Okay, so outer relation is taken as reserve. So M is here. We know that there are 1000 pages in the outer relation, right? Okay, now suppose there are 100 pages in the that is 100 page blocks. Okay, we are breaking this particular relation into how many page blocks? Is the 100 page. Okay, so given this particular equation, we have 1000 plus 1000 is the M, right? What is N? Number of relation of the number of pages in the S. It is 500, right? So it is 500, and then you have the 1000 divided by 100. Okay, so you get, what is the value? 1000 plus 500 into 10. Okay, so this is 5000, so you have the 6000 IOs has to be done to get this particular, this is the total cost, that is the unit 6000 IOs for this particular algorithm to execute the query. If the relation R is the outer relation with 1000 pages, okay, you are using a buffer space of 100 pages, and the relation S is of 500 pages. So given that you have 6000 IOs required. Okay, now suppose if there is instead of buffer space 100, if we consider the buffer space to be 90. So what will happen if we consider the buffer space to be 90? So how many times the S scanning will be required? Scanning of the S relation will be required. Now it is the size of relation R 1000 divided by 90. Okay, divided by 90, right? This is what is and 500 is the number of pages in the relation S plus your 1000 number of pages in the relation R. So this is the number of pages in the relation S, number of pages in the relation R, and the total number of scanning of S required for each of the block of R. Okay. Since it is the 90 number of pages are in the block, so we have this one. So now it is 1000 plus 500 into 12. Instead of 10, now we get 12. So you have now 7000 IOs will be required to get the algorithm executed. Okay, given the buffer space little bit reduced than the earlier. Earlier we had 100 pages in the buffer. Now you have 90 pages in the buffer. Okay. Now if we have the relation S, okay, Taylor, suppose relation Taylor is chosen as the outer relation. Okay. If we have the relation Taylor as chosen as the outer relation, we know that relation Taylor has n is equal to 500 pages, right? R has m, the relation R has 1000 pages. Okay. Now, given this condition, for each of this particular block, because now we are breaking this up into the blocks. Okay. If we have the 100 page blocks, then it is how many time the relation R has to be scanned for each block of S? It is 500 divided by 100, right? 500 divided by 100. So it is the, and we have for this particular, because we are reading this, for each, that is the number of times that relation R has to be scanned is nothing but this much number of time the relation R has to be scanned. Okay, plus 500, that is the number of IOs that has to be performed to get the relation S in terms of blocks, because we have the number of all the pages of the S has to be brought into the buffer block by block. Okay, so this much number of scanning of the relation R is required, right? This much number of scanning of relation R is required, and plus 500. So what we get here is nothing but 500 plus 1000 into 5, right? This is 5000. So 5500 number of IO operations, total IO operations required to execute this particular operation given the block size of 100. Okay. Now, if the block size is of 90, okay, if the block size is of 90 instead of 100, so what will happen is that the same equation, only 100 is reduced to 90. Now we have 1000 into 6 plus 500. Okay, so total IO required if the block size is 90 is 6500. Okay, so IO increased little bit, right, by 1000 for this particular if we reduce the block size. Okay.